Hi, did you hear about the neutron star and black hole collision that scientists observed for the very first time a couple weeks ago? Well, they used gravitational waves to detect it. And what about dark matter? Ever wondered why it's dark? Let's discuss these interesting physics questions. Then we'll drift on to the Sundarbans. Whose land is that anyway? And finally, we'll catch up with India's rivers. Too many are drying up and way too soon. I'm Annie and this is Research Bytes, your dose of science news. When I think of this neutron star black hole merger, it reminds me of that song by Muse, Neutron Star Collision. So far, we can't physically see this collision happening, but scientists have detected gravitational waves from a possible neutron star black hole collision that's thought to have taken place about 1.2 billion light years away. So how did they detect these gravitational waves? Two LIGO observatories in the US and a Virgo facility in Italy picked up these gravitational waves. So what is a black hole? It's this region of space where gravity is so strong that nothing, not even light, can escape it. And a neutron star, it's an extremely dense object. It's as dense as the nucleus of an atom, but it's only made up of neutrons. So when these two massive objects merge in space, they give rise to these gravitational waves. Gravitational waves are ripples in space and time, and there is incredibly high energy event. I think the first time they detected gravitational waves was when two black holes merged. So while we don't know whether there will be a visible counterpart to this black hole neutron star event, we know where to look. Scientists have narrowed down the possible target area in our sky to around 3%. Now, they're busy doing simulations and calculations to try and figure out more about this event and what exactly we should look for and expect to see. And apart from Virgo and LIGO, many countries, including India, have joined the race to explore more of these gravitational waves. India's proposed LIGO India or IndiaGo, which is the Indian Initiative in Gravitational Wave Observations, is scheduled to start operations in 2024. Indigo is a collaboration between LIGO and a consortium of Indian institutes. Well, LIGO will provide the design and the key detector components, while the Indian side will provide the infrastructure to install it at a suitable location in Maharashtra. Exciting, right? Who knows what our Indian observatories could show us in the future. Almost a century ago, Edwin Hubble made a surprising observation: galaxies move apart. And the galaxies that are further away from us seem to be moving faster than the nearby galaxies. With this, he showed us that the universe is ever expanding, and towards the end of the last century, scientists discovered something even more surprising. When they studied how fast nearer and farther galaxies are moving away from us, they found that the universe is not just expanding, but the rate that it's expanding at seems to be increasing. This is as weird and surprising as tossing a ball upwards into the air, only to discover that instead of slowing down, the ball speeds up. So what could be causing the expansion of the universe to accelerate? Normal matter can't do this, so we need to introduce a hypothetical substance, something that has the properties that are necessary to cause the expansion of the universe to accelerate. And scientists call this dark energy. We don't really understand or know what dark energy is, but we've sort of inferred some of its properties. We know that it's something that uniformly fills an otherwise empty space. And yes, it's what causes the expansion of the universe to accelerate. But since the density of dark matter is insignificant in our meager measurements of meters and kilometers, it's difficult to detect in a lab. We can only observe its effects on the scales of clusters of galaxies or even larger. The simplest type of dark energy is called the cosmological constant, and it was introduced by Albert Einstein in 1917. After we discovered that the universe is expanding, this constant was no longer necessary. But since then, it's been revived in the light of new observations of the accelerating expansion of the universe. As our universe expands, the density of ordinary matter seems to decrease because there's only so much of it occupying vast amounts of space. The density of the cosmological constant dark energy, on the other hand, remains constant in space and time. Quantum theories, that's the physics of the very small, seems to sort of suggest that this cosmological constant energy density might exist when it's associated with the vacuum. It turns out that the application of quantum theory on small length scales suggests that an amount of cosmological constant energy density should be much larger than what we've measured dark energy density as. Maybe the density of dark energy has been varying across the evolution of the universe. And if its density changes with time, that makes it dynamical dark energy. So what does this suggest? This means that it's produced in an independent field and it's detached from the properties of space. The inference is sort of that this energy slowly changes with time and gets less and less dense. But we can't be sure whether dark energy is constant or dynamic. There are several experiments like the ground-based dark energy survey and the space-based Euclid telescope that are designed to study this, but we won't really know till the results are in. These experiments try to map out the positions of distant objects like galaxies to better understand their distribution across the universe and kind of infer its expansion history from this. A much earlier phase in the evolution of the universe underwent a rapid expansion called inflation. So picture this. You're adding cold milk to hot coffee. Initially, both of them have very different temperatures. But once the milk is added to the coffee, the particles begin to mix. And with enough time, this whole mixture creates the same temperature. But in the universe, the milk and the coffee seem to achieve the same temperature even though there isn't enough time for them to mix. So how is this possible? Well, one answer that scientists found unsatisfactory is that maybe the initial conditions were the same all around. That means that the coffee and the milk were somehow at the same temperature to begin with. But we can't establish this as a fact, and so we've ruled it out as a possibility. A more satisfactory solution is what's called inflation. In the beginning, different parts of small regions of the universe could communicate with each other and the particles could mix. So each of these small regions could become uniform. At a later stage, the universe underwent a period of rapid expansion called inflation. This greatly expanded these small regions, with one of these small regions eventually growing large enough to encompass the whole of the universe that we observe today. But inflation also predicts that the universe is nearly flat. And what this means is that two parallel rays of light will continue to stay parallel and never converge or diverge over a long distance. This is consistent with results from observations of cosmic background radiation from the early universe. But a slightly spatially curved universe can't be ruled out yet. While inflation is consistent with the evidence we've observed, our current measurements lack the precision that we need to properly test this idea. Cosmology is the study of the origin and the evolution of the universe. It's at an exciting phase today, with unprecedented breakthroughs like the discovery of gravitational waves, which can help us measure how far distances are in space. Just a few weeks ago, we took the first ever picture of a black hole using these gravitational waves. So hopefully in the near future, we'll figure out how to detect gravitational waves from when the universe was young. And this will shed more light on the fundamental questions about dark matter. What is it made up of? What is the geometry of space? Is it flat or just very close to being flat? And is this dark energy density constant or does it vary with time? Who knows? Only time will tell. A water shortage and a growing population equals a recipe for disaster. And while it may cost you your plate of biryani, for many others, it's their livelihood. Rice is a staple food for over 3.5 billion people across the world. And traditionally, rice is grown by puddling water in a field. It's a very water-intensive crop. A mounting pressure to conserve water in agriculture makes rice an obvious target because it requires about 4,000 to 5,000 liters of water to produce a single kilogram of this grain. This is why researchers across the world are making rice varieties that consume less water and can grow in non-puddled fields with aeration. This kind of rice is called aerobic rice. Very recently, researchers from India identified the genes that help aerobic rice adapt to water-scarce conditions. They sequenced and quantified ribonucleic acid or RNA that's found in the cells of the rice plant to reveal the genetic mechanism of a cell at the molecular level. What they found was that the root system of the rice was important in acclimatizing the plant to aerobic conditions. These are all the things that the plant would have to face in a water-scarce environment. A transcription factor gene called DREB1F produces 1.5 times more proteins in an aerobic condition. Then there's the transporter gene for inorganic phosphate. It expresses 4.4 times more in the aerobic variety. And there's also a root trait associated gene that expresses almost threefold more in the roots of the aerobic variety. These genes can help the plant to adapt to a water deficient condition and will pave the way for others to genetically improve rice and help this plant cope with water scarcity. Plus, hormones like ethylene and abscisic acid that are found in the plant make rice more drought tolerant. This study is the first to unravel the genetic mechanism behind the adaptation of rice to aerobic conditions. And for a country like India, that's the second largest producer of rice with half of its rice cultivated land under irrigation, this study gives us hope that in the future, we will not have to starve as water scarcity grips the world. Here's an excerpt from Amitav Ghosh's book, The Hungry Tide. The way he describes the Sundarbans transports you right to its very heart. But here in the tide country, transformation is the rule of life. Rivers stray from week to week, and islands are made and unmade in days. In other places, forests take centuries, even millennia to regenerate. But mangroves can recolonize a denuded island in 10 to 15 years. Could it be that the very rhythm of the earth were quickened here so that they unfold at an accelerated pace? Beautiful, isn't it? I fell in love with the Sundarbans while reading this book. The Sundarbans is an ever-adapting, ever-changing environment that hosts an unparalleled biodiversity. And almost a quarter of India's population, including indigenous tribes or Adivasis, have for centuries lived in and around these forests. They depended on this land for their livelihood. But when the British enacted laws to bring the forests under the ownership of the state, these communities lost their homes, their livelihoods, and their rights. Way back in 2006, the government implemented the Forest Rights Act. This was passed to assert the claims of these communities over their forests. But after more than a decade, do these communities finally have the right to these forests? Well, their reality seems to be very different. First, let's look at what this Forest Rights Act really is. It's supposed to give traditional forest-dwelling communities the right to live in these forests, to use them for agriculture, and to collect non-timber forest products like honey. Tribal communities also have the right to make decisions about the forest and biodiversity conservation. This act empowers Gram Sabhas, which are the local authorities at the village level, to oversee forest management and decide on community and individual claims to forest land. In a study, researchers looked at the implementation of this law in the Sundarban Biosphere Reserve. This is the largest estuarine mangrove forest in the world, and it's shared between India and Bangladesh. What this study found was rather disheartening. The bureaucracy and local elites, like forest workers and the regional political leaders, had very vested interests, and they denied the tribal communities their rights to the forest. The state still made decisions regarding matters related to the forest in violation with the Forest Rights Act, and the bureaucrats prevented the tribals from accessing these forests. The indigenous didn't even know about their rights and entitlements, and they weren't active in local politics. This was something that the local elites took advantage of. Political party leaders also prevented NGOs from conducting awareness camps for these locals. What's truly sad is that the tribals were denied their rights in the name of conservation. Officials often cited that human activities are already stressing out the Sundarbans, and if they implemented the Forest Rights Act, this would further damage the forest. Ironically, it is illegal activities by these local elites themselves that have caused considerable damage to the ecosystem. Powerful politicians pay regional party offices to set up eco-hotels to attract tourist revenue and pay people who work in the forest department to uphold their electoral interests. This tourism in a fragile mangrove ecosystem increases pollution and harms the health of these forests. There's so much more that this study covers in addition to this. I'm focusing on just one part here. The study highlights how politics has prevented the Forest Rights Act from ever seeing the light of day. In a nutshell, bureaucrats and vested interests have snatched away the legal rights of the forest-dependent tribals. This is something that should be making headlines, but it's constantly being swept under the rug instead. And only a large public outcry can help correct this injustice. Some of the greatest civilizations to ever grace our history books flourished alongside riverbanks. From the rivers of Babylon to the Harappan civilization. But India's booming economy, rapid urbanization, and its industrialization have disturbed the ecology of our rivers. Dividing up river water by building dams and exploiting the groundwater resources has reduced the flow of our rivers by leaps and bounds. In a recent study, researchers uncovered how human activities affect the ability of the river catchments to cope with climate change. Most rivers in peninsular India are rain-fed. Water that discharges into the catchment feeds these rivers, and a part of it goes back into the atmosphere. When a catchment becomes drier, a larger portion of the precipitation goes back into the atmosphere, and this decreases the runoff. river catchments are affected by human activities and climate change. So, unless a river is resilient and can bounce back to normal, it gets stuck in this cycle, becoming drier and drier until eventually they ebb away. The results of this study show that only 23 catchments out of 55 are resilient to climate change. While around 60% of catchments that are affected by climate change are resilient, the ones that are closer to human settlements take longer to bounce back. Most of these are from the eastern and upper southern parts of India, whereas the ones in the western parts are non-resilient. So what can we do to protect India's lifelines? Planting grass, shrubs or trees can help control soil erosion. We can conserve water using techniques like pond or roof water harvesting. And better forest management is extremely important in mitigating the negative impact that human activities has on India's rivers. Thank you for listening. The links to all my references can be found in the description below. And if you like this podcast, you can find more science-based stories, podcasts, and news on our website www.researchmatters.in.